So we understand the shape of a given band from the tight binding model and see that the width of the band is related to the strength of interactions between nearest neighbors. This is tall. The bigger this interaction, the wider the band width. We also understand how the group velocity of the electrons goes to zero at the Brillouin zone edge. In order to take this a little further, I need to describe to you the nearly free electron model of band structure. In this model, one considers an electron in which, rather than having a big perturbation torr, the perturbation is very weak, so that the first order description is indeed a parabola. Now, if you imagine that we go to the Brillouin zone here, since we know the properties are periodic, every time you go through 2 pi on A, i.e. between minus pi on A and pi on A, and that we reflect the wave when we reach the Brillouin zone, why then this region here that lies outside the first Brillouin zone can be just as well represented by moving it over here. And if we remember that the edge is curved around in the presence of perturbations owing to band structure, we would then draw something like this, and then here we would draw something like this, and then we would move this one over here outside the first Brillouin zone, back into the first Brillouin zone, and so on. And so one then develops a series of bands. This gap was set by this interaction parameter torr. In the nearly free electron model, 2 torr corresponds to a quantity delta U, and this gap is 2 delta U. So there are a series of bands then that could be occupied by electrons separated by gaps of 2 delta U. In the example I just gave, we had 1 electron per atom, and remembering that we fill up k-states from the lowest in energy until we have used up all the electrons. With 1 electron per atom, we fill up half of the available k-states because we could put 2, one spin up, one spin down. This will put the Fermi energy, in this case, in the middle of this band. And what this means is that there are states available for electrons to go into if you apply an electric field. So a half-filled band gives us a metal. Now, what happens if we have 2 electrons per lattice point? And so we have to fill up all of the available k-states. We fill up to the edge of the band. We now have a full band. Well, what happens next depends on the value of 2 delta U. If 2 delta U is very much greater than kT, we have an insulator. And remember that the number of electrons getting promoted over this thermal gap goes as e to the minus 2 delta U over kT. And so if 2 delta U is a very large number relative to kT, then the number of electrons thermally promoted into the next band up, where they have somewhere to move, can be infinitesimal. This is the primary reason for the enormous spread in resistivity value of materials. Now, an interesting thing happens if we have 2 delta U approximately equal to kT, because now electrons are facilely promoted from this full band into an empty band. In this case, we have a semiconductor. Something else interesting happens in this case also. Let's consider then what happens when we have this band full, let's say, and this band here essentially empty, and 2 delta U being on the order of kT. we will promote electrons from the top of the band in this region here and leave behind unfilled states. So electrons at the top of this band now have a place to go to, and of course electrons in this almost unfilled band have places to go to as well. One can show the quantum mechanical expression for momentum that the mass of a particle is given by 1 over h bar squared times d2 e dk squared. This is trivially true for E equals h bar squared k squared over 2n. Whoops, I better solve it the right way, for -1. We're going to call this, though, the effective mass, because that's what it is. Notice that in this region here, where the parabola looks like that for a free electron, one might expect the effective mass to be something like a free electron. But in this area here, the curvature changes sign. So something that has a positive effective mass here becomes a negative effective mass for particles near the Brillouin zone boundary. What does this mean? Well, if you think about a particle up here in energy, if you accelerate it, the slope of this line gets less as you approach the Brillouin zone boundary, eventually approaching 0. These particles slow down as you accelerate them. That's the meaning of a negative mass. So in Newton's law, we can talk then about a negative mass, or we can talk about a positive mass, providing we change the sign of the force. And since the force is just the charge times the electric field, this is the same as changing the sign of the charge. The charge is negative, so this means that the intrinsic charge is plus E. Carriers moving in this region correspond to a motion that looks as though they are positively charged. They are called holes. So in a semiconductor, current is carried by electrons in a conduction band that is mostly empty, and by holes in a valence band that is mostly full. Finally, a little more interpretation of what these bands mean. So, showing things again in the reduced zone scheme, we can relate each of these bands to atomic orbitals in an isolated atom, whereas we bring neighbors closer to it, we form bonding and anti-bonding states that themselves then split up as we bring more neighbors in, eventually leading to this description of what looks like a continuous spread of states. These series of bands then correspond to the series of states on the individual atom, and so on. And this is the meaning of this index n in our psi n. So we might talk about an S-like band, and then we will describe its eigenstates in terms of the phase from cell to cell, and this, therefore, is the explanation of the two indices we use, one a band index, the second a value for the wave vector k.